I would like to tell you more about loop quantum gravity. Let me skip introduction because, well, anyway, there are some restrictions in time, and usually when I start with introduction, I never end. So it's better if we just. I will just tell you how. Maybe I would like to discuss some basic steps of loop quantum gravity. So this may be my introduction. So this is connection frame variables, and this is mainly due to Ashtekar, but Ashtekar was following others like Klebański, Penrose. Another step is loop variables, and next step is quantum representation. So probably this last step will contain many other points, and it will be the main part of my talk. I could fill this schedule with more details, but as I said, it's better if I get started as soon as possible. So let me still save some space on and here loop variables, of course, Rovelli, Smolin. Okay, so where are connection variables from? Maybe for some to be mathematically exact, at least at the beginning, let me introduce some terminology which I will be using. So M is some four-dimensional manifold. We will endow this manifold with metric tensor, but we do it in this way that there is some other Minkowski space, some flat Minkowski space. So V is a 4D vector space, and it is endowed with some metric tensor. So eta is a metric tensor, and it may be either of signature minus plus plus plus, and then we say that sigma is -1, or it may be of signature plus 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 plus, and then I say that sigma is 1. Okay, and on this, we know that connection and frame variables actually have existed for a long time in gravity. For instance, in Palatini formulation, we introduce E can be introducing Penrose's index notation. So maybe here I should introduce more. So I will denote elements of this space by this kind of index, and this metric will have this kind of index, while here the tangent vectors will have such index. So we use a orthonormal frame, which can be thought of as a one form which takes values in this vector space. So we introduce orthonormal frame. We also introduce a connection one form, which is well, to see that this is a connection, we have to rotate this frame, and then we see how omega transforms, and then it transforms as a connection. And then the Palatini action for this is maybe at some point I will start skipping correct coefficients, because that would take me a lot of time to each time make sure that I didn't make any mistake. J K L J omega K L, where omega is the curvature of this connection. So we have this Palatini action. However, now it turns out, from the point of view of the present loop quantum gravity, that it is convenient to turn this Palatini action actually to Holst action. So P should be replaced by Holst by subtracting from this by introducing some parameter beta and subtracting integral which doesn't change the Einstein equations and can be always subtracted or added if you want, where beta is right. So what is beta? Beta a priori is a number. It may be a real number, but actually so we consider the following possibilities for beta. So beta may have this property that, depending on signature, it may satisfy this equation, which means that in this signature we can choose beta equal to plus minus I, and in this signature beta equal to plus minus 1. And then okay, so maybe I should say examples. So one example is when we choose beta like this. Then if we choose, in this case, this action takes an even nicer form, namely we can write this action as the integral of some self-dual or anti-self-dual two forms and anti-self-dual connection, where and curvature of certain anti-self-dual connection, where in this case we define omega plus is by definition 1/2 should say ij is by definition 1/2 omega ij minus 1/2 beta epsilon ij kl omega kl, and similar definition for sigma plus 1/2 e I which e j. Could you can I erase it? Can I lift somehow this? So do you think this is T1 or T2?
The travel has left the room.
Huh?
You want to go up?
Yeah. Okay, I think I know what to do. No, stop. Okay. Okay, so this is a very nice special case when this is a very nice special case when we choose beta to be either plus minus 1 in Euclidean signature case or plus minus I in Lorentzian signature case. Then this action takes a very nice form. It is just written in terms of self-dual. Self-dual in the sense of those internal indices, which takes values in this V. So self-dual two forms and self-dual and curvature of self-dual connection. And this is the way original Ashtekar variables were defined. And in Euclidean space, those variables would be perfect. However, if we consider real gravity with Lorentzian signature, then and here we take for beta, we take I plus minus I, then we obtain a complex valued action for real gravity. So this is already it leads to some additional constraints. And later we encountered also some obstacles in constructing the quantum theory. So even though this approach is geometrically much better motivated, or maybe algebraically by this relation between geometry and spinors, somehow it turned out that if we consider Lorentzian gravity, then apparently we prefer to consider beta just a generic real number. And actually there is even a special case of beta which Abhay Ashtekar and many people specifically consider, namely, let me give it example number 3, namely beta, which is defined as a solution to certain equation. So consider the following equation. This is going to be sum with respect to half integer numbers that are not 0. Okay, and what we are summing is e to minus 2 pi beta. Beta is unknown in this. It will be an equation, and beta will be unknown, times square root m times m plus 1 equals 1. Okay, so beta, which we consider in loop quantum gravity in some quantitative results, actually satisfies this equation. And you can even write how much it is. I think it is beta equals 0.2375. Yeah, so this equation comes from a consistency between loop quantum gravity and Bekenstein-Hawking formula for the entropy. So if we construct some model of black hole horizon, so we don't really solve exact full theory. We make some model which simplifies a description of black hole, and so this model was introduced by, actually some people who introduced this model are even here, by Ashtekar, who is not here, Ashtekar, Baez, a relative of famous Jean Baez, and Krasnov. So they introduced a black hole horizon model, and later me and my student, and later Meissner we actually calculated exactly the entropy defined by this model, and we found that for the consistency, beta has to satisfy this funny equation. I may comment on this equation more. I just wanted to confuse you a little already at the beginning, because this stuff is so simple. So I wanted to show you something which is actually not clear. Okay. Okay, so in this generic case, so as I said, the modern loop quantum gravity relies on this case 2, or even specialized to case 3. In this case, the structure of those variables is not so nice as in the self-dual case, but still you can easily write the symplectic form, symplectic 2 form for the theory. So given an action, it's very easy to propose symplectic 2 form. In our case, so maybe I introduce some terminology. So we consider gamma is by definition space of solutions E omega such that variation of action is 0. So this is space of solutions to Einstein equations, if you want. And now by delta 1, delta 2, I denote 2 vectors tangent to this space at some solution E omega. So technically speaking, delta 1 and delta 2 are represented by some delta E and delta omega ij, where those fields satisfy linearized Einstein equations, because being tangent to space of solutions to the Einstein equations, it amounts to being a solution to linearized Einstein equations. So actually using this symbol, variation symbol here, is a little misleading, but this is to make connection with physics. In physics we always consider, in Hamiltonian framework, we consider variations. So one can think this, but they are finite. They are not infinitesimally small. And this symplectic form, well, it should be somehow distinguished from that omega which we used there, acting on 2 tangent vectors, can be derived from this action as minus beta integral. And now, okay, so to define a symplectic form, we have to assume something global about space-time. So now we assume that space-time is globally hyperbolic. So it is like sigma times r. It admits global Cauchy surface, and then on this Cauchy surface we write J. So this is variation of this, and by the known Leibniz rule, we obtain those fields which are already defined here, which delta 2 omega omega ij minus beta divided by 2 epsilon I j kl omega kl. And here's some anti-symmetrization, and it should be, yeah. So what does it mean that we have a symplectic form? It means that we can talk about Poisson brackets, we can do canonical quantization. Simply this way of writing symplectic form just makes our framework independent on choice of this surface along which we integrate. So we can choose this surface, we can choose some other surface, but this form is invariant with respect to choice. Modulo some, if we ideally, if sigma is compact, then everything here is precise. If sigma is not compact, then we may run into problems. Then there may be some infinities, or there may be necessary to introduce some boundary terms. If this region is, for instance, bounded by a black hole on one side, then we like to introduce some boundary term. But this is the part which gives you the Einstein equations in symplectic form. Okay, so by using this kind of symplectic form, regardless of whether we consider this one of those special cases, or if we consider any of those other cases, we end up with canonical variables, certain a I and p I b, which so they give rise to the symplectic form So just by defining properly A and P, A as a pullback of this connection and P as a pullback and turned into a vector density, we obtain such form, and in this way we derive our canonical variables. We can see in what way they are. Perfect. So in this way, if we comparison with standard variables, which would be EI orthonormal triad and KAB, this extrinsic curvature on sigma. So in comparison with those variables, our AI is gamma IA, where this is just the Levi-Civita connection of this triad, written in some special basis, minus sigma beta KIA, where I should also explain in what way I raised this index. There was space-time index, and I turned it into this internal, but you can guess how to do it. And my canonically conjugate variable. So here I use again this sigma. Let me remind you, sigma was minus for signature, minus plus plus plus, and plus one plus for signature plus 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 plus. So this is this. In Lorentzian case we have plus, and in Euclidean case we have minus. And P is related in this way to this frame in the following way, that if I here give, so maybe I didn't mention that kappa is 8 pi g divided by c to power 4. So if I multiply this by kappa beta, then what I obtain is it would be an orthonormal vector field. However, this is a density, so it contains also square root of determinant of where Q is E I E J. Well, it's just orthonormal, so we can just contract those indices like this. So at the end of the day, we obtain canonical variables for general relativity in form of connection and canonically conjugate vector density. And now, if this was one of those self-dual cases, then this would be just a pullback of self-dual from the point of view of internal indices, self-dual part of connection or anti-self-dual part, with arbitrary, in general case, this is just a funny combination of Levi-Civita connection of E. So by the way, this gamma is just satisfies D E plus gamma is 0. So it is just derived from this E. And P is a densitized vector, and a most natural, geometrically, the most natural use of E is to turn it into a two form. So we take 1/2 epsilon A B C P C I, and this kind of object is not anymore a density, it's just a two form. A two form. So this is a natural object defined from this. So yeah, okay. So this completes the point 1, which was writing relativity in terms of in terms of connections and triads. Okay, so now the second point of
you also have these two blackboards.
Yeah, but I'm not sure if I was sitting at your talk there, and I couldn't see anything on this blackboard. So. Okay, but I was also sitting at Carlo Rovelli's talk, and he wrote something. Yeah, true. And he wrote something here, and I didn't see it. So those blackboards are my enemies since the. Right, so the second step is quantization, and since we have now, but maybe I should also getting too technical, but this is a part which one has to understand. I mean, one has to at least mention to understand why we do what we do later. That in this theory, if we use those variables, the original host action takes, if we introduce some suitable coordinates, then it takes this form dt aia minus, that would be Hamiltonian, but Hamiltonian is a combination of constraints. Where those are Lagrange multipliers. This is lapse, shift, and one more related to rotations of the frame. So, in particular, it follows from this that Hamiltonian of the theory is integral of those last three. And each of them is a constraint. So it means that we have gauge transformations in our theory. So, and now this constraint generates diffeomorphisms. This constraint generates rotations of frame. And this last constraint is most interesting. It generates evolution in direction orthogonal to Cauchy surface. And each of them is a constraint. So the second step is quantization. But we are looking, okay, so we want to quantization of, one may say, quantization of the following Poisson relation, Poisson bracket. So we would like to quantize the following Poisson bracket. However, we cannot use the standard techniques because we are interested in diffeomorphism invariant theory, and this is some new element for this kind of canonically conjugate variables. There are diffeomorphically invariant connection theories like Chern-Simons theory, but then the Poisson structure is different. So the idea was to use those loop variables, which I actually skipped because this was my point number 2, but skipping the loop variables and going to quantization of loop variables. The proposal was the following. So let us first formulate what is our starting point. So since A is a connection, so we have some principal fiber bundle P, which is projected to our sigma, and with structure group G. In the framework, it is a compact Lie group, and actually it is SU2, but our framework works well for a compact group, and it doesn't work well for a non-compact group. That's why we were not able to use SL2C instead. Maybe somebody can fix it in future. So we have a principal fiber bundle over sigma, and we have A is space of connections And now our quantum state it should be some function. Should be some functions. I mean, we're looking for quantization where quantum states are functions of connections. That means that, naively speaking, operator corresponding to this is just evaluation of A, or while operator corresponding to P is just h bar divided by I variation with respect to A. However, still this didn't help much. So we understood this idea. So Smolin and Rovelli introduced those loop variables, and mathematical formulation of that idea was that consider cylindrical functions. So introduce a notion of cylindrical function. So we say that psi is a cylindrical function if psi, the value psi assigns to any connection, is given by holonomy transports of this connection along certain set of paths. So to give you a picture, this is our bundle. This is not space-time anymore. This bundle, it has more dimensions. It has 6 dimensions. This is sigma. These are fibers. And now here in sigma, I have some path. And given a connection, this path defines automorphism between two fibers which correspond to the ends of this path. And this automorphism is APA, and we are interested only in functions which are functions of those automorphisms. So now it turned out that actually it is possible to simplify considerably those considerations if we follow suggestion of Roger, who is here. So I was in Syracuse, Roger was visiting. I went to Roger and I asked, what can I assume about curves to ensure that curves can intersect or overlap in some way I can control? And then Roger said, assume analytic category. Okay, so let us assume additional assumption that M is analytic, or maybe sigma is analytic, and everything is analytic, what I'm talking, so all those paths are also analytic. And then it turns out that, okay, so now I will pass to this blackboard because there's not much time. So if we assume okay, maybe I still continue here. So if we assume analyticity, then it turns out that for every bunch of paths I can think of, there exists a graph which contains all those paths, and actually they are even even in some even way. It means they are compositions of links of this graph. So if we assume there's analyticity, then for every finite set of paths, there exists a graph such that maybe I'm not sure whether I did it. Okay, so we can invert our procedure. We can first fix embedded. So in sigma, we fix some embedded graph, and then we consider only paths contained in this graph. Then we consider a different graph and the same, and we consider the family of all embedded graphs. So using this idea is consider the set of gamma, where gamma are embedded graphs. Now, what is nice about those embedded graphs is that if we introduce a quite natural relation between them when this graph is finer than another one, then they satisfy the following, that for every pair of graphs there exists a graph which is bigger than both of them. So in this way, our set of all cylindrical functions was decomposed as a set sum of cylindrical functions defined only on graphs. And then the solution of our problem to construct the Hilbert space was to endow each graph with a measure in such a way that whenever two spaces overlap, then the measures agree. And we found examples of such measures, and actually there was one example which was much simpler than all others. So those are with some consistency, which we call cylindric consistency. It together defined a notion of integral which had very nice properties. It was diffeomorphic invariant. It was invariant with whatever it had to be invariant, however, still in analytic category. And also it was faithful in the sense that whenever function was not zero and positive definite, then the integral was also not zero. So that gave us the, let me just write this one more symbol, so at least we have Hilbert space is L square on the space of connection with this measure.
You want to see how is this measure called?
I have no idea what people call it. And the spin networks which Carlo was talking about, they just define an orthonormal basis in this Hilbert space, which is particularly convenient in definitions of operators and in using this defining states.
I think it's a good point to stop because we're running late for lunch. Unfortunately, they told me that we should hurry up. So let's thank you.